Okay, looks like got at least most people with us from the waiting room. So before we go into this question, a couple more joining us, just remind you where we are. So when we left off on Monday, I'd been talking about the glomerulus specifically, but we'd also covered some of the basic terms we want to remember when we're thinking about the kidney, specifically the nephron. Okay, so those terms, right, were filtration, right? So things moving out of the plasma into Bowman's space, which is part of our renal corpuscle. We talked about reabsorption, which is things moving out of the filtrate, so out of the nephron and back into the bloodstream. And we talked about secretion. So secretion is things moving from the bloodstream later on in the nephron, moving back into the fluid in the nephron. Okay. So we're starting from the top of the nephron, which is at the renal corpuscle and the glomerulus. So the glomerulus is basically some capillaries. So we have an afferent arteriole coming in, right? Afferent meaning two. Then we have the glomerulus, which is a bunch of loops of capillaries. We have all these loops really because we want to make sure we have a lot of surface area, allowing to filter out really everything that's in that plasma other than the proteins and the red blood cells. So we want to make sure we have enough time and enough space to do that. And then the blood flow continues, becomes the efferent arteriole, which is narrower because we want blood flow to kind of back up in those glomerular capillaries, again, to give them more time to filter out everything that's in the plasma. And then that efferent arteriole would go on and form our peritubular capillaries and our vasa recta, which we'll talk about later. So the other part of the glomerulus we were looking at was Bowman's capsule and Bowman's space, which is basically like a cup around these capillaries. So I'm going to form this sort of layer here, like this. So we got kind of a mouth eating our glomerulus. So this is the beginning of the nephron. So this is what we're talking about. The place we're going to talk about our Starling's forces as being relevant for our nephron, for our kidney. So I'm going to delete my little picture of the nephron because we now have a nicer picture from our textbook. Okay, so the Starling forces that we talked about when we're talking about capillaries, and now again when we're talking about filtration in the nephron, come in two basic types, right? We have our hydrostatic forces, right? We have our hydrostatic forces, and we have our oncotic forces, right? So hydrostatic forces, remember, are basically coming from our idea of the pressure exerted by like a water column. So the hydrostatic forces, that hydrostatic pressure, is basically the pressure of blood pushing out on these capillary walls, or the pressure of fluid in the space pushing on its respective walls, which in this case would be pushing back towards the capillaries. Oncotic forces are a pull exerted by proteins, basically. So if we want to think about our oncotic forces, right, we're going to think about all these proteins that we're still leaving in our capillaries, right, because proteins are not getting filtered in the glomerulus. They're staying in those capillaries. So those walls, those fenestrated capillaries, let almost everything through, but not proteins. So the fact that we're like concentrating these proteins down means there's going to be a pull of water towards them. The same thing would happen with any solutes that are in Bowman's capsule. They would exert a pull in this direction. We don't really really have them much because those proteins are really staying in the glomerular capillaries. So that's the kind of big picture sort of kind of conceptual way we're thinking about these, but we can detail them a little more scientifically and use very specific terms, all right? So glomerular capillary hydrostatic pressure. Glomerular, we're saying that this is a pressure coming from those glomerular capillaries. So we know it's going to be something about this section here in red, right? So it's something about these. Specifically, it's its hydrostatic pressure. So it's the pressure of the blood in those capillaries. So then we think in our minds, okay, so which direction is pressure of the blood in the capillary pushing us, right? So we have a push. So we know blood pushes out, right? Pushes out on the walls. Okay. If we look at the direction of that arrow, we know filtration is the movement of fluid into the nephron, right? So we can see that our arrow for that hydrostatic pressure, that push on the wall of the capillary, is going in the direction that we've defined as filtration, right? So filtration is this initial movement of fluid and solutes out of the blood and into the beginning of the nephron. So our glomerular capillary hydrostatic pressure is favoring filtration because of the direction of that arrow. Now the other force for filtration, so the other thing that would give us an arrow in the same direction, it's not going to be a push, it's going to be a pull, right? So basically for both filtration favoring filtration and opposing filtration, we have one push and one pull. For these forces opposing, we also have one push and one pull, right? Okay, so our pull that gives us an arrow going into the nephron would be the pull of the solutes that are here in Bowman's space, in Bowman's capsule. So capsule is this kind of mouth that's eating our glomerulus. So they're exerting a pull on water. So they'd be pulling water towards them to come water them down. That's going this filtration direction. So our Bowman's capsule oncotic pressure, so oncotic, the pressure of any proteins, be favoring filtration. All right. I want you to note this equation down here in the right, we can already start to fill in, right? We know that the way we calculate an overall kind of net filtration pressure is we take our forces, I'll use the typing tool, our forces for filtration, and we subtract our forces against filtration. So here we have forces for filtration, and then we're subtracting our forces against filtration. So if we look at what we're doing here in this equation, we'll note that this first force is our glomerular capillary hydrostatic pressure, which is PGC. All right, so that's about 60. So that's the highest number that we have in this equation. So we know that that pressure of blood in those glomerular capillaries is really the main driving force for filtration into our nephron. Okay, and if we compare that against our other force for filtration, the Bowman's capsule oncotic pressure, or this pi BC, right? We know pi is for oncotic pressures, right? So that's our second term. You can see that that's because there really are no proteins dissolved in this space. So if there were proteins hanging out here in Bowman's capsule, then they would exert a pull towards themselves. But under normal conditions, we shouldn't have proteins there because they can't cross that barrier for filtration, which is composed of our capillary endothelial layer, basement membrane, and then those podocytes, that sort of modified epithelium that makes up the sort of layer that's surrounding those capillaries and leading into Bowman's capsule. Okay, so we would put it in our equation, but we won't actually have a value there because we shouldn't have proteins. So then our forces against filtration, I'll just clear all, right? Our forces against filtration is going to be anything that's pushing us back towards those capillaries, right? If filtration goes this direction, opposing filtration goes that direction. Okay, so anything going back. So we're going to be looking for a push and a pull. Most obvious thing is the pull back towards the capillaries, right? So we know these capillaries are keeping all their proteins. So they have a lot of proteins there. So that pull of the proteins is going to go in this direction. The other thing, our push back towards the capillary, is going to be exerted by any of our fluid here in our Bowman's space, inside this Bowman's capsule. It's going to push out on the walls. So that push is going to direct fluid back towards the capillaries. Okay. So our values for that, we'll start with that hydrostatic pressure, Bowman's capsule, right? Hydrostatic pressure is PBC, right? So that's about our push. So P for push, we can kind of think, right? So our push, our hydrostatic pressure here is about 15 millimeters of mercury. Right, so it's lower than our push of fluid being filtered out of the capillary, but it does exist. So there is fluid in Bowman's capsule. So we do put a number to that. Right? Same thing for the glomerular capillary oncotic pressure. So our pi is for our pull. So this is our pull of the proteins in the capillary. All our proteins really should be staying in that capillary. So our value, much higher than our 0 that we had before when we were talking about proteins in the capsule. So that pull back towards the capillary, we have a value of 29. So that's a force opposing filtration because it's pulling things back towards the capillary. So if we do this equation out, we get our typical glomerular filtration pressure. So the glomerular filtration pressure, or GFP, is basically the net filtration pressure that we had in the capillary, but now we're being specific that we're talking about a glomerulus. So glomerular filtration pressure is the sum of the Starling's forces for filtration minus the sum of those forces opposing filtration. It's usually 16. But we'll see that as we change these things, particularly as we change our blood pressure and therefore change pressure in the glomerular capillaries, we will see variations to glomerular filtration pressure, and therefore we will see changes to the glomerular filtration rate. Questions about these different forces before we move on, because like when we talked about them last time, they're pretty important.
Could you clarify again the PGC, what that's pushing on?
Yeah, absolutely. So I'm going to clear my scribbles first. So the PGC, the glomerular capillary pressure. So what we're saying is we're talking about the blood in the capillaries. So that's the first part. And then we're talking about the hydrostatic pressure. So hydrostatic, right, has that hydro part. So we're talking about water. So it's the pressure of the water in the plasma in the capillaries. And basically, if we have more fluid in the capillaries, right, it pushes out on the capillary walls because, you know, if you put a lot of fluid, right, like imagine you have a hose and you're forcing a lot of water through these capillaries, right? Like as you put more and more, those walls would have to expand to fit it. So they're exerting a pressure out on the walls, right? Like that's why if you increase it, those walls would have to kind of stretch. So their force is for filtration because they're pushing out on these walls. As they push out on these walls, we can just kind of lengthen the arrow because as they push on the walls, we know that this membrane is kind of leaky, right? This barrier for filtration is not all that much of a barrier, right? We know that blood is getting filtered really fast through the kidneys. So as that water presses out on the walls, a lot of it actually goes through them and escapes into the nephron. Does that make sense?
Yes, thank you.
Okay. Anybody want to go over any of these other ones? Okay. I think our slide is just a zoomed in version of this calculation for the glomerular filtration pressure so that you have it in your notes. Yeah, and we can talk about these one more time, just in a differing sort of set of words, right? Okay, so we have forces favoring filtration and we have forces opposing filtration, right? And now they've drawn them out for you. Again, slightly neater than my drawing. So in these drawings, we have our big proteins in green, basically, and we have our little water molecules in blue. So our forces favoring filtration, we can see these blue molecules are water molecules inside the glomerulus. They're pushing on the walls. So those pink arrows are basically the water moving out of those glomerular capillaries into Bowman's space. So that is our capillary hydrostatic pressure. And what we're also noting on this slide is the fact that the efferent arteriole is narrow. So a quick kind of heads up on different drawings or different pictures of this nephron. Don't pay attention to like whether the efferent or afferent arteriole is on top or on bottom, because the position of nephrons in the kidney is not like 2D. So pay attention to which one's wider and which one's narrower. So the wide one on our previous slide, I think, was on bottom, but here it's on top. Maybe that's not right. Maybe they're consistent, but the wider one is always your afferent arteriole in these drawings. And the narrow one, right, so narrower in diameter, is your efferent arteriole. And the efferent arteriole is narrower. And so we know when we have a smaller radius, that raises resistance. So we have really high resistance in this efferent arteriole, which basically causes like a backup of blood in these capillaries. So that's part of why this pressure is so high. It's because as the blood gets backed up, right, we're putting more and more blood into this same space, but we're not letting it escape. So that just raises the pressure of the water pushing out on those walls. So the other force for filtration, not flavor, the other force for filtration, not really significant. We don't have proteins in the filtrate, so that's 0. But just to make sure that we actually talk about every possible force, it counts as a force favoring filtration. So the forces opposing filtration are the capillary hydrostatic pressure, which does exist. So we can see that we have a lot of these blue water molecules in this capsule in Bowman's space. So they do push back towards the capillary. It's relatively high, like 15 is not 0, but it's nowhere near as high as the force in the capillaries. Okay. So we do have a lot of filtrate in there. It's just that we have so much blood in the glomerulus that this is not going to overcome the force for filtration. Okay. A glomerular oncotic pressure we do have because it's the pull of these green proteins. So there is a pull towards them. So pulling sort of filtrate back towards the capillary. This is higher than in systemic capillaries as well, because as we lose fluid into the filtrate, so as water molecules actually do move out and into the nephron, this kind of concentrates our proteins. So it's higher than the values we saw when we were looking at net filtration in the capillaries as well. Yeah, and here's the zoomed in equation. So we're just linking it up to the numbers, right? When we want to calculate out, we have our forces favoring filtration minus our forces opposing filtration is going to equal our filtration pressure, or our GFP, as you will see it abbreviated. So that's all we're looking at there. And so we have now paired up our numbers. Our PGC, so the capillary hydrostatic pressure, is 60. We have 0 for our Bowman's capsule oncotic pressure, but we want to put it in for thoroughness. We're subtracting our forces opposing filtration. So subtracting that pressure of the filtrate pushing back towards the capillary. So the Bowman's capsule hydrostatic pressure. We're also subtracting the pull of the proteins in the plasma, which are pulling filtrate back towards them, or more formally, the glomerular capillary oncotic pressure. So that's what we do when we calculate our glomerular filtration pressure. I'm circling this because we're going to talk about how we calculate a couple different things. So this is very specifically for the pressure. We're also going to be talking about the rate and the filtered load. So remember that the glomerular filtration pressure is the one that's like the net filtration pressure that we did before. So that brings us to the glomerular filtration rate, which is our GFR, so rate. So just from that word rate, we know something about the units, which can kind of help us remember what this is, right? So rate means we're going to have an amount over a period of time. So specifically, glomerular filtration rate is usually going to be measured in milliliters per minute, because that's just a value that gives us reasonable, easily interpretable numbers for the glomerular filtration rate. Okay. So our typical glomerular filtration rate, we want to compare to the renal plasma flow. So when I say that, what I mean is that our renal plasma flow, this first thing we're talking about, this is talking about basically how much blood goes through the kidney every minute. So the total amount of blood passing by, like going through this pathway, right, in the afferent, out the efferent, right, that typical flow overall, we have 625 milliliters going through that loop every minute. Right? So that's the blood we have going to our nephrons. Our glomerular filtration rate, our next number, the filtration rate, is how much of that is moving into the nephron. So how much of it actually gets filtered out. So we can see that not all the plasma is getting filtered out immediately, right? It's not like we have our blood flow here and then stop, no more blood after it goes through the kidneys. We don't use it all up. We don't actually filter all the plasma immediately ever. So it's a lot, but it's not all of it. So it's 125 milliliters typically, which does give us 180 liters per day, which is a lot more liters per day, or a lot more liters than we have liters of blood in a human. So we already know that we're going to have to do a lot of reabsorbing because this is just not physically possible. Okay. So our filtration rate is 125 milliliters. Our renal plasma flow is 625 milliliters. And on this picture, it's super helpful, right? We can see that the blood going in, 625 milliliters. We have filtrate coming out, 125 milliliters, which means that leaves us with 500 milliliters of plasma leaving the kidney every minute. All right, so these two add up, right? Now, compared to our systemic capillaries, right, this is a really high filtration rate. All right, so our filtration rate here in our normal systemic capillaries is only 3 liters per day, right? So if we compare these two values, we can see how crazy high the filtration rate for the glomerular capillaries is. So that has partially to do, right, with this filtration pressure, right? And it also has to do with the fact that this barrier on the capillaries is quite permeable. So this filtration pressure of 2 was the filtration pressure we got back in our normal systemic capillaries, which we compare, right, to our glomerular filtration pressure. We know that the glomerular filtration pressure, which we just calculated, much higher, right? We had 16. Okay. So what we do with this glomerular filtration rate, we're going to use this filtration rate both to calculate our filtration fraction, which is going to tell us basically like what percent of the blood, what percentage of the plasma is getting filtered through the nephrons every minute. We're also going to use this glomerular filtration rate to help us calculate how much of a solute is going to be getting filtered through the kidneys as well. So we're basically doing 2 calculations with this number. So the number we're focusing on here is this 125. All right, so we're going to see this value of 125 over and over again as we're doing our calculations. Okay. So the first calculation we can do with this GFR, this glomerular filtration rate, is our filtration fraction. So the filtration fraction is actually usually expressed as a percentage, not as the actual fraction, but it's super simple. All it's telling us is like what percent or what fraction of the blood is being filtered into the kidney. So we calculate that literally as a fraction, right? We take the amount in the kidney, which is 125. We take the amount that flowed to the kidney, which was 625. We just do the math, right? So if you divide 125 by 625, that gives you 0.2 or 20%. So that is our typical normal filtration fraction for our kidneys under normal states. So here you can see calculated out here. It's also calculated out here. Now, what we can also do with this GFR, the GFR being 125, is calculate the filtered load of small molecules. So our filtered load, so load, think like how much filtered is filtered into the kidneys. All right, so what we're going to do is we're going to take that glomerular filtration rate, that 125 milliliters a minute, and all we're going to do is multiply that by the concentration, right? So we're just going to multiply that by the plasma concentration for whatever molecule we're tracking. And we often do this with glucose specifically, but we can do it with other molecules as well. So to calculate our filtered load of glucose, all we would do is take that typical glomerular filtration rate of 125, and we're just going to multiply it by our concentration of glucose, right? Concentration of glucose. And that'll give us the filtered load of glucose. All right, so we're seeing how much plasma is being filtered, how much glucose was there in the plasma, then we'll know how much glucose is filtered. So it's pretty straightforward. It just has a special name. Okay. So here we see that calculation at the bottom. So the typical plasma concentration of glucose is 100 milligrams per deciliter. Now to actually do this calculation, which I believe you did way back in Phys 1 lab. So to do this calculation, you're going to take this 100 milligrams per deciliter. You're going to convert the units because we know that our GFR is in milliliters per minute, right? So we don't want deciliters and milliliters. Those don't go together, right? We can't multiply together our different units like that. So we convert our 100 milligrams per deciliter for glucose concentration into milligrams per milliliter, because that's how we have our GFR rate. So then we multiply that, right? So here's our GFR, just as we saw it before, our 125 milliliters per minute, multiplied by our plasma concentration of glucose, which we've converted so that it's also in milliliters. Super conveniently, that just gives us 1. Right, so the filtered load of glucose under these conditions, if your blood glucose is 100 milligrams per deciliter and your glomerular filtration rate is 125 milliliters per minute, would just be 125 milligrams per minute. So that's telling you how much glucose is getting filtered into the kidney every minute. Okay. Before we move forward, any questions about these 3 calculations we've just done, which, reminder, were the glomerular filtration pressure, the filtration fraction, and the filtered load? I think the main thing here is going to be making sure that you can tell those 3 terms apart. I think the calculations for them are hopefully fairly straightforward once you think through them. So again, a moment that I'm going to plug using flashcards, just so you can tell these 3 apart. Okay. So cyclomerular filtration rate is clear, should be, usually is, about 125 milliliters per minute, which comes out to 180 liters per day. We're going to want to regulate that filtration, right? Just like we regulate all sorts of things in our body. One of the things that we're going to see, one of the reasons that we do want to regulate that glomerular filtration rate, is that when we have the glomerular filtration rate, it kind of sets us up for basically the correct amount of reabsorption in our nephron. So even though we have this filtration rate of 100 liters per day, you only excrete, so about 125 liters of urine. So you're not peeing 100 liters per day. So we're going to be reabsorbing a lot of fluid. And now you can imagine if you suddenly had a lot more fluid going into the nephron, right? Like if your kidneys are not getting 180 liters per day, but they're getting 200 liters per day, 500 liters per day, something like that, you can imagine how it might disrupt just some of the mechanisms that your kidney has for doing appropriate reabsorption and appropriate secretion of solutes back in. Okay. It's actually true that a very small increase in the glomerular filtration rate would lead to a really large volume of fluid and large increase in the volume of fluid, and therefore also a large increase in the amount of fluid being filtered out and excreted. And that's because that 125 was per minute, right? So if 125 per minute goes up at all, right, you have to multiply it out, or a lot of minutes in a day, right? So you wouldn't have to have that big an increase in GFR in order to get to a really crazy number of liters of fluid per day. So we do highly regulate that glomerular filtration rate because we don't want to lose a ton of fluid. Because if we lose a ton of fluid, then basically we're going to end up losing blood volume and therefore really messing with our blood pressure. So the kidneys are actually super important for managing blood pressure overall. Okay. So here we see that relationship between the filtration rate and our mean arterial pressure. All right, so our blood pressure basically and our filtration rate. So pressure is on the x-axis here. Right, our mean arterial pressure, our filtration rate is over here on the y-axis. So here we have our typical 125 milliliters per minute, our filtration rate. Right? And we can see that there's actually a nice big range of mean arterial pressures where we have that same glomerular filtration rate, right? So this whole range, I'll actually take it up to like 180, right? This whole kind of range of mean arterial pressures is the part where our normal kind of, our normal regulatory mechanisms work really well to keep us at the appropriate glomerular filtration rate. We can see if we get outside of this zone of mean arterial pressures that we do see the filtration rates start to either shoot up or fall down. So these areas outside of this range are where our regulatory mechanisms are going to have trouble, and we are really going to have impacts on the filtration rate and therefore on fluid loss, and therefore kind of doing a feedback loop on the arterial pressure due to the effects on blood volume. So we can handle a number of pressures, but we want to stay kind of in the middle here. Okay. Which brings us to regulation. So just like for a lot of our other processes in physiology, we have intrinsic and extrinsic regulation of the glomerular filtration rate. So we're going to number them 1, 2, 3 for our intrinsic regulation. All right, I got our 3 bullet points. So our 3 types are 1, myogenic regulation. So we know from the myo, this is going to have something to do with muscles. 2, we have tubulo-glomerular feedback. So tubule, it's got something to do with tubes, right? Glomerular also has something to do with the glomerulus. 3, Messangeal cell contraction. All right, so we're going to need to remember what a Messangeal cell is. Okay, so we'll go through each of these. I'm just helping you out, circling some words in the terms to help you remember for later, right? Like actually just looking at the term kind of tells you what it is. Okay, so starting with the myogenic regulation, the myo part, the specific muscle we're talking about, is the smooth muscle in our afferent arteriole. Okay. So just like other arterioles throughout the body, like when we talked about our systemic circuit, right? Our afferent arteriole, remember we want to find the bigger one, which is here on bottom, right? Bigger in diameter, it tells us that's the afferent arteriole. So you can see it's got its layer of smooth muscle cells, right? Just like other arterioles, right? We really want to be able to regulate resistance in arterioles overall. So myogenic regulation, what happens is that smooth muscle can contract. So just like other places we see smooth muscle, when that muscle gets stretched out, right, it wants to bounce back. So if it stretches out too much, it's going to contract in response. In order to understand what that means for our glomerular filtration rate, it's kind of helpful to think out why that muscle would stretch out, right? So I'm going to just kind of walk us through it. We will have one of those flow charts near the end of the lecture, or potentially to tomorrow or Friday. But I like to do these things with pictures. Okay, so in order to stretch out that smooth muscle, right, the conditions under which that smooth muscle is going to get stretched, really going to be when we have lots of blood flowing in, right? So stretch is going to be caused literally by blood, right? By blood pushing out on capillary walls, which we talked about when we talked about Starling's forces, but that's really just what blood does to walls of vessels, right? So increases in blood pressure create an increase in that force pushing the walls of arteriole out. And that is what is stretching the muscle surrounding the arteriole, right? So under these conditions, before we have the bounce back, right? If we just have high blood pressure and we have lots of blood flowing in, that means we would have lots of blood flowing through these capillaries, flowing through our glomerulus, flowing through those glomerular capillaries, right? And if we have more blood, right, say instead of 625 milliliters, we had like 800, right? That would also raise the value in milliliters of how much fluid is getting filtered out of the plasma and into the glomerulus, right? So if we kept our filtration fraction at like 20, right? 20% of 800 is more than 20% of 625, right? That's just math. Okay. So we would be losing more fluid in terms of milliliters if we raised this pressure and raised the speed of blood going past. So what happens in the myogenic regulation is, in order to prevent this, we have the muscle bounce back, right? So the muscle constricts, right? The muscle constricts. This means we don't have as much blood flowing into the glomerulus. So that blood flow is slowing down. It has less pressure. It has less pressure. So that glomerular filtration pressure is going to go down, because it was really being driven by that glomerular capillary hydrostatic pressure. So I'm glad we went over the hydrostatic pressure twice, right? That was a really good idea to ask a question about that one in specific, right? So as we increase resistance in that afferent arteriole, that hydrostatic pressure from the capillaries goes down, which means that we don't have as much glomerular filtration pressure overall, right? We don't have as many forces for filtration anymore, which means we're going to have less of our plasma getting filtered into the Bowman's capsule. So that was big and long, and like I said, we'll have a flow chart. But that's why this regulates our GFR, right? It's kind of a long series of steps to understand how this process works. Okay, so our second type of feedback of regulation is the tubulo-glomerular feedback. And we'll talk briefly about this again when we actually talk about the tubules part of this. But this has partially to do with the structure of the nephron, right? So I'm going to draw very quickly, right? So we have our afferent arteriole. I'll match the picture so it's on the bottom. We have our glomerulus. We have our efferent arteriole. It's going back, creating peritubular capillaries, vasa recta, etc. I'm not going to continue drawing that. What I want to draw on is our nephron. So our nephron starts with Bowman's capsule, all right? We then have our proximal convoluted tubules. So they're kind of squiggly. We then go into the loop of Henle. We're going to talk about what each of these are doing, but right now it's just important to kind of know the positioning. And then we have our distal convoluted tubules. They're coming back towards the beginning, basically, as they're doing their squiggle thing before they dump into the collecting ducts. So when you're looking at the actual well-drawn picture down here, right, the textbook picture, you're not looking at the full thing. We have the glomerulus and Bowman's capsule here. They haven't drawn the rest of the nephron, but it would like squiggle off over here, go into the loop down here, and then come back. So what you're looking at here is actually the ascending limb of the nephron loop. So the ascending limb of the loop of Henle. Okay, so this part of the nephron So already had a lot of the fluids and other contents of the nephron reabsorbed. We've done a lot of fiddling with the contents of the fluid here in the tubules. So the fluid here is going to have different concentrations than this fluid that we immediately filtered out at the beginning. This part of the nephron is where we have these specialized macula densa cells. So we talked about the juxtaglomerular complex before. So the macula densa cells were the ones that are part of this kind of terminal portion of the nephron. So they're in purple here. And the macula densa cells, they're basically feeling how much fluid is passing by them, right? And they're going to release paracrine factors. So this is basically a cell signal, right? So cell signal to local cells. And the local cells that they are signaling to is the smooth muscle of the arterioles. So they're releasing paracrine factors, and you can see that they're kind of nestled here between our efferent and afferent glomerular arterioles. So they're going to be sending out paracrine factors that are going to affect the smooth muscle in both of them. And they're going to create constriction in these arterioles, right? So basically, they're responding to the fact that, for example, blood pressure has risen. So the glomerular filtration rate went up. We have tons of fluid going through the nephron. So it's coming really fast, shooting past these macula densa cells. And they kind of sense that there's too much fluid there, that it's too fast. So they say, hey, slow down. And they're saying, hey, slow down to those muscle cells surrounding our arterioles. So as they constrict, they raise resistance of the arterioles, both coming in and going out. And that overall slows down the blood going through the glomerular capillaries. So it kind of makes it seem like the blood pressure in those capillaries is lower. So that slows down and decreases our glomerular filtration rate. The final thing on here is our mesangeal cell contraction. So your book refers to this kind of in two ways. One way is it says that this is decreasing the permeability of those capillaries. But then when it goes into detail, it gives you a little more of what it means on that. So our mesangeal cells, right, are right here kind of next to our macula densa cells. So they're right here. And they are kind of a modified smooth muscle. So they also respond to stretch. So they're also kind of sensing what's going on here in this juxtaglomerular complex. And if we have an increase in the fluid, it's also going to affect these cells, and they're going to respond by contracting. What happens when they contract is essentially they're kind of turning off some of these capillaries. And as they do that, right, if this blood in the glomerulus is only flowing through a couple loops instead of tons and tons of loops, there's less surface area and almost less time for filtrate to get out. So because it's those cells that are kind of turning off these capillaries, it's also going to have the effect of decreasing the amount of fluid that gets filtered because we don't have enough surface area kind of for as much of it to get filtered as it usually would. Okay, sorry, and I realize we're 2 minutes over time, so we'll stop here and talk about extrinsic stuff on Friday.
Thank you.
Take care, everybody.